Welcome to a definitive masterclass on graph theory. Whether you are a university student, a competitive programmer, or just someone who loves the hidden structure of the world, this video is designed to take you from zero to mastery. We aren't just looking at dots and lines, we're exploring the mathematics of connection. We're going to cover the entire landscape, starting with a core notation and the fundamental handshaking lemma, moving through the DNA of graphs like isomorphisms and diving into the famous puzzles that started it all, like the 7 bridges of Königsberg. We'll finish with the heavy hitters, planarity, and the laws of graph coloring. Because this is a masterclass, we're covering a lot of territory. I've organized the video into navigable chapters, which you can find in the description or the progress bar below. If you're looking for a specific topic, like adjacency matrices or Hamiltonian cycles, feel free to jump straight there. But if you're here to build a rock-solid foundation, I suggest we start right at the beginning. So let's get started. If you'd like to support the channel, you can now become a member to get early access to every video. To join, you can use the link at the top of the board or just hit the join button right below this video. In this tutorial, we're going to explore the world of graph theory, one of the most powerful tools in modern mathematics and computing. Essentially, a graph is a mathematical structure used to model a set of finite pairwise relations between objects. When I say pairwise, I simply mean a relationship that exists between a pair of objects. It's all about describing exactly how things are connected. Think about a GPS system, and let's assume the diagram on the left is its graph. If I wanted to get from city A to city E, there might be several different routes I could take. My goal is usually to find the shortest path. To do this efficiently, we use a level of abstraction, which means that the unnecessary details are removed, like the specific name of every street or the number of traffic signals along the way. By stripping these away, the focus is entirely on the connections required to get from A to E. This effectively simplifies a complex real-world problem into a clean, logical structure. Looking at the graph I've built for our GPS example, you can see the different pieces of this relation. I can go directly from city A to city E, or I can take an alternative route, traveling from A to E via cities C and D. Another way would be to go via city B, and if I wanted to go a way that took in all the cities, I could go via cities B, C, and D. In the language of graph theory, each of these cities is represented as a vertex, or vertices in the plural. The lines connecting them, representing roads or paths, are called edges. When we define this mathematically, we describe the graph as an ordered pair, and we write it as G equals V comma E, where the V and the E are in parentheses. This means that the set of vertices must be defined first, because the edges depend on those points existing. Let's look at how we write this out in formal notation. First, we have our vertex set, denoted by capital V. This is simply the set of all objects in our system. In our GPS system, that set is represented as V equals A, B, C, D, and E. Note the curly brackets here. This means that it is unordered. And so this is identical to the set where V is equal to E, D, C, B, and A. And using this notation, duplicates are ignored. Next, we define the edge set, denoted by capital E. This describes the specific connections between those vertices. For our graph, the edge set looks like this. So E is equal to AB, AC, AE, BC, BD, BE, CD, and DE. And once again, the notation of curly brackets means that these pairs are unordered. The power of this notation is that it gives us a blueprint. If we're given a set of vertices and a set of edges, we can build a graph schematically. We don't need a map. We just need the logic of the sets to draw the structure. Now that we can define a graph using sets and draw it schematically, let's look at how we measure the importance of each point in our network. Not all vertices are created equal. In our GPS example, a major hub city will have more roads leading into it than a small rural town. We describe this mathematically as deg v. The degree of a vertex is simply the number of edges connected to it. If we look back at city B, it has 4 edges leading out of it. We say the degree of vertex B is equal to 4. It's a simple count that tells us how connected that specific piece of the graph is. In graph theory, one other type of structure worth mentioning is a loop, or self-loop, that connects a vertex to itself, which we can see in this diagram, where vertex C connects to itself. So if A, B, and C were cities, this type of route would begin and end at the same city. So in this case, C. And so in terms of mathematical notation, we can see the vertex set V contains A, B, and C, and the edge set E has unordered connection AB, AC, and CC. And this particular one denotes the loop. Now that we understand the basic structure, we need to look at different types of graphs. We can categorize these based on their specific properties, essentially how relaxed or strict the rules of connection are. First, we have the simple graph. As the name suggests, it's the simplest form of graph, and it contains no loops and no multiple edges between the same 2 vertices, which means only single lines between the vertices. In this example, we have 4 vertices, A, B, C, and D. And the edge set shows that we have connections between A and B, A and C, A and D, B and D, and C and D. If these rules are relaxed, we get a multigraph. This allows for multiple edges between the same vertices, but still no loops. Think of this as having 2 different roads connecting the same 2 cities in our GPS example. In the example on the board, we have a multigraph with 4 vertices, A, B, C, and D. And as you can see, there are 2 edges between vertices A and B. So the edge set looks something like this. So E equals AB, AB again, to account for the multiple edges between A and B, AC, BD, and AD. An alternative way of writing this is to show the edge set as having edges E1, E2, E3, E4, and E5, where E1 is AB, E2 is AB, E3 is AC, E4 is BD, and E5 is AD. If we go a step further and allow both multiple edges and self-loops, we call this a pseudograph. And the example on the board shows a pseudograph. Note the multiple connections between vertices A and B, and also notice that vertex B has a self-loop. So in this example, we have vertices A, B, C, and D, and the edge set shows that we have connections between A and B again to account for the multiple connections, A and C, B and D, A and D, and B and B. B and B accounts for the self-loop. This can also be written as the edge set is equal to E1, E2, E3, E4, E5, and E6, where E1 is AB, E2 is AB, E3 is AC, E4 is BD, E5 is AD, and E6 BB. Next, let's look at the direction of a graph. In undirected graphs, like our GPS example, the edges have no arrows. The connection is a two-way street, and hence the notation we use is curly brackets, simply because the order doesn't matter. And so in our edge set, each connection is enclosed in curly brackets. So we can have a connection between A and B, but the order of that connection doesn't matter. So it's just as relevant to have a connection between B and A. In directed graphs or digraphs, like the one shown here, the edges have arrowheads, meaning it's a one-way relationship. We must use parentheses in the edge set for these because they are ordered pairs. In the diagram shown here, the order is specific. The edge set is a single direction only. So we have a connection from vertex A to vertex B, but not the other way, from B to A. Essentially, this is a one-way street. In weighted graphs, every edge has a numerical value associated to it. In our GPS example, this represents the cost of the path, such as the distance in kilometers, miles, or the time it takes to travel. A number linked to the edge is shown on the graph, as shown here in the diagram. In unweighted graphs, as shown here, every edge is considered equal. There are no values. We only care whether a connection exists or not. We can also classify graphs by how reachable the vertices are. A complete graph is a network where every single vertex is directly connected to every other vertex by exactly one edge. So the diagram here shows a complete graph. All the vertices are connected to each other. And in graph theory, the notation we use for this is K4, where 4 indicates the number of vertices in the graph. In a complete graph, K subscript n, we can use the formula where m is equal to n into the bracket of n minus 1 divided by 2 to calculate the number of edges. In this case, n is the number of vertices and m is the number of edges. In our example here, where we have a complete graph denoted by K4, n is equal to 4. We have 4 vertices, A, B, C, and D. So the number of edges m is equal to 4 into the bracket of 4 minus 1 divided by 2. So the number of edges m is equal to 6. While this might not seem so useful with a graph such as the one on the board, where it's very easy to count the number of edges, when we have complicated graphs, this kind of formula is essential. A graph is said to be non-complete if there is at least one pair of vertices that are not directly connected by an edge. So in this diagram, we can see that vertex B is not connected to vertex D, vertex B is not connected to vertex C, and vertex A is not connected to vertex D. So this graph is said to be non-complete. In a null graph, we have a collection of vertices, as shown here as A, B, C, and D, but absolutely no connection between them. So they have no edges. So in this case, the edge set is empty. A special type of null graph is known as a trivial graph. This type of graph must have exactly one vertex and no edges. So again, the edge set is empty. Let's now test our knowledge on graphs by looking at some examples. In this first example, let's see if we can identify the type of graph and write out the vertex and edge set. So pause the video now if you want to play along. So as we can see, this graph has 4 vertices, A, B, C, and D. We note that vertex A and vertex B are connected with a single edge, as are vertex A and C. However, vertex C and D have 2 edges between them. And we also note that none of the edges in the graph have arrows. So this makes the graph an undirected multigraph, and its edge set is A to B, A to C, C to D, and again C to D. And these last 2 make it a multigraph. Note that all edges have curly brackets surrounding them, and this tells us that it's an undirected graph. In this example, we're given the vertex and edge set, and we want to draw the graph. So pause the video now if you want to play along. And so the vertex set indicates that we have 4 vertices, A, B, C, and D. And if we look at the edge set, first thing we can notice is that they're all in parentheses. That means that this is a directed graph. So we have an edge between A and B, A and C, B and D, A and D, and C and D. We have a total of 5 edges, and they all have arrows on them. And the graph looks like the diagram shown on the board. And in this example, let's see if we can identify the type of graph and also calculate the number of edges without actually counting them. And again, if you want to play along, pause the video now. In this graph, all vertices are connected to each other by edges. That makes it a complete graph. We note that it has 6 vertices, so the graph is denoted as K subscript 6. We can also see that none of the edges have arrows, so that makes it an undirected graph. To find the number of edges, we can use the formula where m is equal to n into n minus 1 divided by 2, where n is the number of vertices and m is the number of edges. In this case, n is equal to 6, and therefore m is equal to 6 into the bracket of 6 minus 1 divided by 2, so m is equal to 15. Without counting and using this formula, we can tell that the graph has 15 edges in total. I have a challenge for you. You're building a network with 7 servers A to G. Your boss wants every single server to be connected to exactly 3 others. Simple, right? Let's try and draw it. So we can start with server A and connect it to server B. We can also connect it to server C, and let's connect it to server F. The server A is now connected to 3 servers. Let's move on to server B. Server B already has 1 connection to A, so let's connect it up to server C. And if we also connect it up to server D, then server B has 3 connections. So if we move on to server C currently has 2 connections, 1 to A and 1 to B. So if we connect it up to server E, then server C now has 3 connections. And moving on to server D, this at the moment just has the 1 connection. If we connect it up to server E, it now has 2 connections. And connecting it up to server F gives it 3 connections. If we now move on to server E, which already has 2 connections, we can connect it up to server G, and that gives it 3 connections. So now moving on to server F, we see it already has 2 connections. So we can connect it to server G, and that gives it the 3 connections. So all servers, apart from G, now have 3 connections. Server G just has 2 connections, so it needs 1 more. And if we connect it to any other server, one of those other servers is going to have 4 connections. So it's not my drawing skills that are failing me. The network is mathematically impossible. To understand why, we need to understand the handshaking lemma. So the handshaking lemma says that the sum of the degrees of all the vertices is equal to twice the number of edges on the graph. And just a note here, the E with the bars around it does not mean the absolute value of E. It means the number of edges in graph theory. And as the number of edges is multiplied by 2, it means that the sum of the degrees of the vertices must be an even number. In graph theory, every edge has 2 ends. It's like a handshake. 1 handshake, but 2 hands are involved. This means that if you add up the number of connections every person has, that total must be an even one. On the board, I've drawn a complete graph, K3. It has 3 vertices, A, B, and C, and they're all connected to each other. So the degree of vertex A is 2, the degree of vertex B is 2, and the degree of vertex C is 2. So now if we sum the degrees of the vertices, we have 2 plus 2 plus 2, which is equal to 6. And we have 1, 2, 3 edges in this graph. And so according to the formula, the sum of the degrees of the vertices, which in this case is 6, must equal 2 times the number of edges. So in this case, 3. And as we can see, the formula holds true. Now let's go back and look at our networking problem, which didn't work out too well. We have 7 vertices, and we wanted each to have a degree of 3. So if we now apply the handshaking lemma here, where each vertex has a degree of 3, we get 7 multiplied by 3, which equals 21. So for our network to hold true, the sum of the degrees of the vertices, so 21, would have to equal 2 multiplied by the number of edges. So for this to hold true, the number of edges, or the number of cables that connect each server, would equal 10.5. And since you can't have half a cable, the graph cannot exist. Now, what happens if we change our impossible question to an even number of vertices? Let's take 6 servers and give them each 3 connections. So in this case, the sum of the degrees of the vertices would be 6, as we have 6 vertices, and each has 3 connections or 3 edges. So we'd have 6 multiplied by 3, and that would give us 18. 18 is an even number. So according to the handshaking lemma, 18 would equal 2 multiplied by the number of edges. And so we need just 9 edges to make this work. And like our 7 server disaster, this one is perfectly possible. So let's see if we can draw them. So we can connect server A to server B, D, and F. And so server A is now connected to 3 other servers. If we now look at server B, which already has a connection to server A, we can connect it to server C and server E. So now server B has 3 connections. And if we connect server C to server D and server C to server F, this completes the 3 connections for server C. And connecting server D to server E gives server D 3 connections. So we're now left with server E and F, which both have 2 connections. And if we connect them together, each has 3 connections. So as you can see, everyone has 3 neighbors and the maths is happy. So what if we have 6 vertices and every vertex needs an even degree, like 2 for example? So the sum of the degrees of the vertices would be 6 multiplied by 2 because we have 6 vertices and each has 2 edges. So this will give us a total of 12. So the sum of the degrees of the vertices, which would be 12, should equal 2 multiplied by the number of edges. And so the number of edges should equal 6. Let's see if we can draw this. So we can connect vertex A to B and A to C. And we can connect vertex B to vertex D and vertex C to vertex E. And finally, we can connect vertex D to vertex F and vertex E to vertex F. So we have 1, 2, 3, 4, 5, 6 edges as expected. And this creates a cycle graph where the number of vertices n is greater than or equal to 3. And every vertex has a degree of exactly 2, forming a single closed loop. We need to be careful because even if the maths passes the handshaking test, it might fail the capacity test. So suppose we have 4 vertices and we want each to have a degree of 5. So the sum of the degree of the vertices is 4 multiplied by 5, which is equal to 20. That's an even number. But the lemma says it's okay, right? Wrong. In a simple graph, you can't have more friends than there are people in the room. If there are only 4 of you, the maximum degree you can have is 3. So you connect to the other 3 people. Even though the sum is even, you literally don't have enough vertices to attach these edges to. So in a simple undirected graph, the maximum degree of any one vertex in a graph is n minus 1, where n is the number of vertices in a graph. Now let's see if we can apply the knowledge we've just learned to some problems. So in this first problem, let's assume you're at a party with 10 people. You count the handshakes and find that every single person shook hands with exactly 3 others. How many total handshakes took place? If you want to play along, pause the video now. So if we think of people as vertices on the graph, we have 10 people and we know that each of them has shaken hands 3 times. So the sum of the degrees of the vertices is 10 multiplied by 3, which gives us 30. And we know that this number is 2 multiplied by the number of edges, which in this case are handshakes. In this case, the number of edges is 30 divided by 2, which equals 15. In this next problem, let's assume we have 5 servers in a network and 4 total connection cables. 3 of the servers are connected in a triangle, each connected to the other 2. So in our diagram, A, B, and C are connected in a triangle. And the 4th server, so server D, is connected to just one of those 3. So D is connected to server C. The 5th server is sitting in the corner with no connections at all. Does the handshaking lemma still work? If you want to play along, pause the video now. So let's see if the handshaking lemma still works for this problem. So firstly, let's look at the degrees of each vertex. So we can see that vertex A has 2 edges. So the degree of A is 2. Vertex B also has 2 edges. So the degree of B is 2. Now we can see that server C is connected to A, B, and D. So the degree of server C is equal to 3. And we can see that server D just has 1 connection to server C. So the degree of server D is equal to 1. And server E is sitting in the corner and it's not connected to any other server. So its degree is set to 0. And if we add these numbers up to get the sum of the degrees of the vertices, we have 2 plus 2 plus 3 plus 1 plus 0, and that equals 8. And the handshaking lemma says that the sum of the degrees of the vertices is equal to the number of edges multiplied by 2. In our case, 8 is equal to 2 multiplied by the number of edges. And therefore, according to the handshaking lemma, the number of edges in our graph is equal to 4. So 8 divided by 2. So let's check that. So we have 1, 2, 3, and 4. In this third problem, we have two graphs, A and B. Each graph has 5 vertices. And in graph A, each of the vertices has a degree of 4. And in graph B, each of the vertices has a degree of 5. The question is, which of these graphs is impossible to draw and why? And if you want to play along, pause the video now. But let's first see if they pass the handshaking lemma. So for graph A, the sum of the degrees is 4 plus 4 plus 4 plus 4 plus 4, which equals 20. And for graph B, it's 5 plus 5 plus 5 plus 5 plus 5, which is equal to 25. In graph A, 20 is equal to 2 multiplied by the number of edges. So the number of edges in graph A is equal to 10. So that's an even number, so that works. And in graph B, 25 is equal to 2 multiplied by the number of edges. In graph B, the number of edges have to be 12.5. So that fails the handshaking lemma. So we know at this stage, graph B is impossible to draw. Let's also do the capacity test. So the maximum degree of a vertex is equal to n minus 1 in a simple undirected graph, where n is the number of vertices. So we have 5 vertices, so 5 minus 1 is equal to 4. In graph A, the maximum degree of a vertex is 4, so it passes the test. And in graph B, the maximum degree of a vertex is 5. The graph B also fails the capacity test. So the only graph we can draw here is graph A. And in the last problem, you're auditing a new social media platform. The database claims that there is a small group of 9 users, and the system says that every single one of them has exactly 5 friends within that group. The manager suggests that there's a bug in the code. Without drawing the graph, can you explain why the manager is right? If you think you know the answer, then please leave a comment in the comment section. In this video, we're going to be taking a close look at subgraphs, isomorphism, and complementary graphs. Think of it like this. Subgraphs are about taking a graph apart. Isomorphism is about proving 2 graphs are twins, even though they look different. Complementary graphs, well, that's the graph of everything that isn't there. We're going to master all 3, but to understand how graphs relate to each other, we first have to understand their shadows. So let's begin with complementary graphs. In mathematics, the complement of a graph G, which we write as G bar, is a graph with the exact same vertices but totally different edges. So if edge UV exists in graph G, then it cannot exist in G bar. And if edge UV does not exist in G, then it must exist in G bar. So on the board we have a graph G with vertices A, B, C and D. And it has edges AB, BC and CD. And it's in the shape of a U. Look at vertices A and B. In graph G, they're adjacent, meaning there's an edge connecting them. So this edge cannot exist in G bar. Look at vertices A and C. Are they connected in graph G? No. So in G bar, we need to include that edge. And if we look at vertices A and D, there's no connection in G. So again, we include an edge in G bar. And in graph G, there is no connection between vertices D and B. And therefore, we need to include it in graph G bar. Now let's check to see if we did this right. If we take the new graph G bar and overlay it on top of our original graph G, we should get a complete graph K4. This means that every single possible handshake is accounted for. So the edges in G plus the edges in G bar. And the union of G and G bar is equal to K4. Now that we know how to find the total opposite of a graph, what happens when we don't want the whole graph? What if we just want a slice or subset of of the original graph. That's where subgraphs come in. A graph H is a subgraph of graph G if the vertex set of H is a subset of the vertex set of G, and the edge set of H is a subset of the edge set of G. So you can't have an edge in your subgraph if you didn't keep the vertices it connects to. It's like a friendship. You can't have a friend if that friend does not exist. So on the board, we have graph G, which has 5 vertices, A, B, C, D, and E, and 6 edges, so 1, 2, 3, 4, 5, and 6. So let's draw graph H, which is a subgraph of graph G. Graph H has 4 vertices, A, B, C, and D, and 4 edges, 1, 2, 3, and 4. According to our definition of a subgraph, graph H is a subgraph of graph G because the vertex set of H is a subset of the vertex set of graph G, as both have vertices A, B, C, and D, and the edge set of graph H is a subset of the edge set of graph G, as both graphs have the edge from A to D, from D to C, from C to B, and from A to B. What would happen if on graph H we added an edge from D to B? Then graph H would no longer be a subset of graph G, even though the vertex set of H is a subset of the vertex set of G. The edge set of H is no longer a subset of the edge set of G. A couple of things that happen when you create a subgraph. Because we are potentially deleting edges, the degree of a vertex in the subgraph will always be less than or equal to what it was in the original. And just because the original graph was one big connected web, it doesn't mean that the subgraph will be. So you can take a connected graph, delete a few edges, and end up with a disconnected graph. Connectivity is not guaranteed. Now let's take a look at a couple of special subgraphs. So first up is the spanning subgraph. In a spanning subgraph, it includes every single vertex from the original graph, but it picks and chooses which edges to keep. So using graph G, a spanning subgraph would be graph H. So we have the complete set of vertices, but we're missing the edge from D to C. The next type of special subgraph is the induced subgraph. This is the opposite of the spanning subgraph, in that we take a subset of the vertices, but once we've selected the vertices, we must take every edge that existed between them in the original graph. So the vertices decide which edges we take. And so using graph G again, an induced subgraph would look something like the one on the right of the board. So we have a subset of the vertices, so we have A, B, D, and E, and we've retained all the edges between those vertices. So we have one from D to E, A to D, and A to B. So we've just seen that a subgraph is like a slice or subset of the original graph, where we pick and choose vertices and edges from a parent graph. So now, what if I have two graphs that look totally different but contain all the same subsets? This is called an isomorphism, and is when two graphs look completely different on paper, but they're actually the same structure. It's like the same person wearing two different outfits. The person, the graph's DNA, hasn't changed, just the presentation. Let's see what needs to match for us to declare that two graphs are isomorphic. So the first thing that needs to match between the two graphs is the vertex count. So both graphs need to have the same number of vertices. Next, we look at the edge count, and the edge count of both graphs need to match. And then we look at the degree sequence of both graphs. So if we list the degrees of vertices of each graph from highest to lowest, they must be identical. So if one graph has a vertex with 4 connections, the second graph must also have the same. And finally, we need to look at the cycles within each graph, and these need to match. Sometimes the vertices and edges match, but the structure does not. This is why we check the cycles. So what do we mean by a cycle? If we start at a particular vertex, pass through more than one vertex by connecting edges, and end up back at the starting vertex, we've completed one cycle. So in our graph G, we can start at vertex A, move to vertex D, then move from vertex D to vertex C, and then from vertex C, and we arrive back at A. And this is one cycle. It's also a triangle. And so if one graph has a triangle and the other graph does not, then they are not isomorphic. An isomorphism must preserve the length and number of each cycle in the graph. And a graph may have a number of different cycles. So we need to show that both graphs have the same cycles. And therefore, if any of these four tests fail, the graphs are not isomorphic. If, on the other hand, all these tests pass, we can prove the isomorphism with a mapping. This is a function that acts like a translator. So we can say, for example, that vertex A in one graph is vertex 2 in another, and so on. So if vertices A and B are adjacent in one graph, then their twins in the second graph must also be adjacent. If that relationship holds true for every single vertex, we've found an isomorphism. If we have an isomorphism between graph G and graph H, we use this notation. So there's an isomorphism between graph G and graph H, and the edge set UV belonging in the edge set of G must map to the edge set belonging in graph H. Now let's use the graphs G and H on the board to test for an isomorphism. So in the first test, we need to show that the number of vertices in graph G is the same as the number of vertices in graph H. So in graph G, we have vertices A, B, C, and D. That's 4. And in graph H, we have vertices 1, 2, 3, and 4. Therefore, the number of vertices matches in both graphs, so it passes this test. Next, we need to show that the number of edges in graph G is equal to the number of edges in graph H. So in graph G, we have 1, 2, 3, 4, 5 edges. And in graph H, we have 1, 2, 3, 4, 5 edges. And so this test also passes as both graphs have 5 edges each. Now let's look at the degree sequence of each graph. And let's arrange the degrees of the vertices of each graph from highest to lowest. So in graph G, we can see that vertex A has 3 edges. Vertex D has 2. Vertex C has 3. And vertex B has 2. And arranging these from highest to lowest, we have 3, 3, 2, and 2. And for graph H, vertex 1 has 3 edges. Vertex 3 has 3 edges. Vertex 4 has 2 edges. And vertex 2 has 2 edges. And arranging these in order from highest to lowest, we have 3, 3, 2, and 2. So as we can see, the degrees of graph G matches the degrees of graph H. So this test also passes. Now let's check the cycles in each graph. So in graph G, we can go from A to D, D to C, and from C back to A. So that's a C3 cycle. We can also go from A to B, from B to C, and from C back to A again, which is another C3 cycle. And then we can go from A to D, from D to C, and from C to B, and then from B back to A. And that's a C4 cycle. Now let's do the same on graph H. So we can go from 1 to 2, from 2 to 3, and from 3 back to 1. And that's a C3 cycle. Then we can go from 1 to 4, from 4 to 3, and from 3 back to 1, which is another C3 cycle. And then we can go from 1 to 2, from 2 to 3, from 3 to 4, and then from 4 back to 1 again. And that's a C4 cycle. So as we can see, the cycles of both graphs G and H match. And finally, to prove that they are the same, we can pair up the vertices which have the same number of degrees. In graph G, we have vertex A, which has 3 degrees, and vertex C, which has 3 degrees. In graph H, we have vertex 1 with 3 degrees, and vertex 3 with 3 degrees. And so we can map vertex A in graph G to vertex 1 in graph H, and vertex C in graph G to to vertex 3 in graph H. In graph G, vertex B is connected to vertex A and C. In graph H, vertex 2 is connected to vertex 1 and 3. And so we can map vertex B in graph G to vertex 2 in graph H. And in graph G, vertex D is connected to vertex A and C. In graph H, vertex 4 is connected to vertex 1 and 3. And so we can map vertex D to vertex 4. Therefore, we've proved that there exists a one-to-one, or more formally, a bijective mapping between graphs G and H, such that adjacency is preserved. Now let's consolidate what we've already learned and look at a few problems. In this first problem, we have a graph with 6 vertices, A, B, C, D, E, and F. We have an edge, AB, BC, CD, ED, EF, and AF. And we want to find the graph's complement. If you'd like to play along, pause the video now. And so to find the complement, G bar, we need to find a graph with the same vertices, but totally different edges. So if an edge exists in graph G, then it cannot exist in G bar. And if an edge does not exist in G, then it must exist in G bar. So for G bar, let's start adding the edges that don't exist in graph G. So we can add an edge from A to E because it doesn't exist in G. We can add edge AD and AC. Edge BE doesn't exist in G, and neither does edge BD. We can add edge FC, FD, EC, and FB. And as a final check, we need to show that the union of graph G and graph G bar is a K6 graph. So that's a complete graph. And so overlaying G bar on top of G gives us our complete graph K6. In this second problem, we have graph G. We have 3 other graphs, H1, H2, and H3. Now 2 of these graphs are subgraphs of graph G, and one of them is not. Can you work out which graph is not a subgraph of G? If you'd like to play along, pause the video now. So to be a subgraph of G, the vertex set must be a subset of the vertex set of graph G, and the edge set must be a subset of the edge set of graph G. So let's examine the graphs one by one. So if we look at graph H1, it has vertices 1, 2, and 3, and these vertices also exist in graph G. Also, it has an edge from 1 to 2 and 1 to 3, and these edges both exist in graph G. So this graph is a subgraph of graph G. For H2, we have vertices 1, 2, 3, 4, and 5, and these vertices all exist in graph G. And looking at the edges, we have an edge from 1 to 2, which exists in graph G, 2 to 3, which exists in graph G, 3 to 4, which exists in graph G, 4 to 5, which exists in graph G, and 1 to 5, which also exists in graph G. So graph H2 is a subgraph of G. And moving on to graph H3, we have vertices 2, 4, and 5, and these all exist in graph G. And we have the edge from 4 to 5, which exists in graph G, and an edge from 2 to 4. Now, if you look at graph G, this edge does not exist. And so H3 is not a subgraph of graph G. In this last challenge, we want to perform the tests to determine whether an isomorphic relationship exists between graph G and H. So first up, we need to show that the number of vertices in graph G is equal to the number of vertices in graph H. And then we need to show that the number of edges in graph G is equal to the number of edges in graph H. So if we look at graph G, it has 1, 2, 3, 4 vertices, and graph H has 1, 2, 3, 4 vertices. So the number of vertices in each graph equals 4, so therefore the same. Now let's look at the edges. So in graph G we have 1, 2, 3, and 4, and in graph H we have 1, 2, 3, and 4. So we have 4 edges in each of the graphs. So the number of edges in each graph is the same. The next thing we need to check is the degree sequence of each graph. For there to be an isomorphic relationship, the degree sequence of each graph needs to be the same. And we check this by counting the degrees of each vertex and then ordering them in descending order. And so the degree sequence of graph G is 2, 2, 2, and 2. That means that each vertex has a degree of 2, so it has 2 edges. And the same is true in graph H. The degree sequence of graph H is 2, 2, 2, and 2. And in the next test, we need to check the cycles of the graph are the same. So a cycle is when we start at one vertex and we pass through more than one and we get back to our original vertex. So in graph G, there's an obvious cycle from A to B, B to C, C to D, and D to A. And this is a C4 cycle. And apart from this cycle, I can't see any further cycles in graph G. So let's see if that cycle is repeated in graph H. So in graph H, we can start at vertex 1 and go to 3, from 3 to 2, from 2 to 4, and from 4 back to 1. So again, we have a C4 cycle in graph H. And again, I can't see any further cycles in graph H. And finally, to prove the isomorphism, we need to show that we can map the vertices of G to the vertices of H. So as all vertices have a degree of 2, let's start by mapping vertex A in G to vertex 1 in H. Now in graph G, vertex A connects with vertex D and B. And in graph H, vertex 1 connects to vertex 3 and 4. So let's map vertex B to vertex 3. So if we look at graph G, vertex B connects to vertex A and C. And in graph H, vertex 3 connects to vertex 2 and vertex 1. So we know that vertex 1 maps to vertex A. So therefore, vertex 2 is mapped to vertex C. And we can map vertex D to vertex 4. And so vertex D connects to vertex A and C. So vertex 4 connects to vertex 1, which is the equivalent to vertex A. And vertex 4 connects to vertex 2, which is the equivalent of vertex C. So therefore, we've proved that there is an isomorphic relationship between graph H and graph G. You've seen the theory. You know that two graphs can look completely different on the page, but actually they're identical twins in the eyes of mathematics. But how do you prove it when the structures get complex? In our previous video, we covered the basic definition of an isomorphism with an example of how to identify and verify one. I've prepared further examples that we're going to walk through together. We'll start by using our intuition to identify the potential relationship, and then we'll move into the formal step-by-step process to verify the isomorphism. We'll be looking at vertex mappings, degree sequences, and even some tricky cycle counts. If you haven't watched the earlier video, I've linked it in the description. But if you're ready to master the verification process, let's begin with this first example. So here we have two graphs, G and H. In graph G, we have vertices lettered A to F. And in graph H, we have vertices numbered 1 to 6. Let's check to see if there's an isomorphic relationship between the two. Firstly, we need to show that the number of vertices in G is equal to the number of vertices in H. And then we need to show that the number of edges in G is equal to the number of edges in H. So in graph G, we have 1, 2, 3, 4, 5, 6 vertices. And in graph H, we have 1, 2, 3, 4, 5, 6 vertices. So both graphs have 6 vertices. Now moving on to the edge count, graph G has 1, 2, 3, 4, 5, 6 edges, and graph H has 1, 2, 3, 4, 5, 6 edges. And so the number of edges in each graph is the same and is equal to 6. Next, we need to look at the degree sequence of each graph. So in each graph, we need to count the number of edges associated with each vertex and then order them from highest to lowest. And for an isomorphic relationship to exist, the degree sequence of each graph needs to be the same. So let's begin with graph G. The vertex A has 2 edges, vertex B has 2 edges, vertex C has 2 edges, vertex D has 2 edges, vertex E has 2 edges, and vertex F has 2 edges. And in graph H, vertex 1 has 2 edges, vertex 2 has 2 edges, vertex 3 has 2 edges, vertex 4 has 2 edges, vertex 5 has 2 edges, and vertex 6 has 2 edges. If we now order the degrees of each vertex from highest to lowest for each of the graphs, we get the degree sequence of graph G and the degree sequence of graph H. And as we can see, both degree sequences are the same. Next, to show that there is an isomorphic relationship between the two graphs, we need to show that the cycles within each of the graphs are the same. So they need the same number of cycles, and each of the cycles needs to have the same length. So to find a cycle, we start at one vertex, travel along the edges to other vertices, and then we end up back where we started. So let's look at graph G. If we start at vertex A, we can travel to B, and then to C, to D, to E, to F, and then back to A again. So in graph G, we have a cycle of length 6. So it's a C6 cycle, and it includes all 6 vertices in graph G. And moving on to graph H, we can start at vertex 1 and travel to 2, to 3, and back to 1 again. And we can also start at vertex 4, travel to vertex 5, to 6, and back to 4 again. And therefore in graph H, we have 2 cycles of length 3, so 2 C3 cycles. So as we can see, we have a different number of cycles between graph G and H, and also the cycles are of different lengths. And so in this case, there is no isomorphic relationship between graph G and graph H. In this next example, we have 2 graphs G and H. Let's check for an isomorphism. As usual, if you'd like to play along, pause the video now. So let's first check that the vertex count and then the edge count are the same in each of the graphs G and H. So the vertex count first. In graph G we have 1, 2, 3, 4, 5. And in graph H we have 1, 2, 3, 4, and 5. And so the vertex count in each graph is equal to 5 and therefore the same. And now moving on to the edge count. In graph G we have 1, 2, 3, 4, 5, 6 edges. And in graph H we have 1, 2, 3, 4, 5, 6 edges. And so both graphs have 6 edges. So the edge count is the same. Next we need to show that the degree sequence of each graph is the same. So let's number the degree of each vertex in each graph. So beginning with graph G, vertex E has 2 edges. So the degree of E is 2. A has 3 edges, so its degree is 3. D has 2 edges, C has 2 edges, and B has 3 edges. And in graph H, vertex 1 has 2 edges, vertex 3 has 2 edges, vertex 2 has 3 edges, vertex 5 has 3 edges, and vertex 4 has 2 edges. And so for each graph, if we order these numbers from highest to lowest, we get the degree sequence of the graph. And as we can see, the degree sequence of graph G and graph H are identical. Next, let's look at the number of cycles within each graph. And remember, the number and length of each cycle needs to be the same. And so beginning with graph G, we can start at A, travel to C, then to B, and from B back to A again. So that's a cycle of length 3. So it's a C3 cycle. And then we can start at A and travel to B, move on to E, and then to D, and back to A again. And that's a cycle of length 4. So a C4 cycle. And then we can start at A again, move to C, to B, then from B to E, from E to D, and then from D back to A again. And that's a cycle of length 5. So a C5 cycle. And moving on to graph H, we can begin at vertex 1, travel to 2, then on to 5, and back to 1 again. And so that's a cycle of length 3. So a C3 cycle. Next, we can start at vertex 2, move on to vertex 3, from 3 to 4, from 4 to vertex 5, and then back to vertex 2 again. And that's a cycle of length 4, so a C4 cycle. We can then start at vertex 1 again, travel to 2, and then from vertex 2 to vertex 3, vertex 3 to vertex 4, 4 to 5, and then vertex 5 back to vertex 1 again. And that's a cycle of length 5, so a C5 cycle. So as we can see, graphs G and H have the same number of cycles, and each cycle is of the same length. And finally, we need to show that a mapping exists between the vertices of graph G and the vertices of graph H. So in graph G, the two 3-degree vertices, so that's A and B, are connected to each other, and they both connect to vertex C. This creates a triangle A, B, C. And in graph H, the two 3-degree vertices, so that's vertex 2 and 5, are connected to each other, and they both connect to vertex 1. And this creates a triangle containing vertices 1, 2, and 5. So therefore, we can see that vertex A maps to vertex 2, vertex B maps to vertex 5, and vertex C maps to vertex 1. In graph G, we can see that vertex A is connected to vertex D, and vertex D is of degree 2. And in graph H, we've already connected vertex 2, which corresponds to vertex A, with vertices 1 and 5, as they make up the triangle. And the remaining vertex in graph H, which is also a degree 2 vertex, is vertex 3. And so vertex D in graph G maps to vertex 3 in graph H. And so the remaining vertices, vertex E and vertex 4, must map to each other. And so we can say that graph G has an isomorphic relationship with graph H. In this example, we have two graphs G and H. Let's check for an isomorphism. And again, if you'd like to play along, pause the video now. So our first test is to check that they have the same number of vertices and that they have the same number of edges. So in graph G, we have 1, 2, 3, 4, 5 vertices. And in graph H, we have 1, 2, 3, 4, 5 vertices. So therefore, each graph has 5 vertices. The number of vertices in each graph is equal. And now let's look at the number of edges in each graph, as these also need to be equal. In graph G, we have 1, 2, 3, 4, 5, 6, 7. And in graph H, we have 1, 2, 3, 4, 5, 6, and 7. And so the number of edges in each graph is 7. And therefore, each graph has an equal number of edges. So next, we can look at the degree sequence of each graph. So we need to order the number of degrees of each vertex from highest to lowest, and the two sequences need to match. In graph G, vertex A has 2 edges, so therefore the degree of A is 2, and vertex B has 4 edges, so its degree is 4, and vertex E has 3 edges, so its degree is 3, and then D has 3 edges, so its degree is 3, and C has 2 edges, so its degree is 2. And then if we look at graph H, vertex 1 has 3 edges, so its degree is 3. Vertex 3 has 3 edges, so its degree is 3. Vertex 2 has 3 edges, so its degree is 3. Vertex 4 has 3 edges, so its degree is 3. And vertex 5 has 2 edges, so its degree is 2. And so for graph G, we get a degree sequence of 4, 3, 3, 2, 2. And for graph H, we get a degree sequence of 3, 3, 3, 3, and 2. And as we can see, these are not the same. As this test has failed, there cannot be an isomorphic relationship between graph G and graph H. In our next example, let's check these two graphs, G and H, to see if there exists an isomorphic relationship. And again, if you'd like to play along, pause the video now. So first, let's check that the number of vertices in each graph are of equal number. So in graph G, we have 1, 2, 3, 4, 5, 6 vertices. And in graph H, we have 1, 2, 3, 4, 5, 6 vertices. So both graphs have 6 vertices and therefore an equal number. And moving on to the number of edges, these also have to be equal in number in each graph. So in graph G, we have 1, 2, 3, 4, 5, 6, 7 edges. And in graph H, we have 1, 2, 3, 4, 5, 6, 7 edges. Each graph, therefore, shares an equal number of edges. Next, moving on to degree sequence. In graph G, vertex A has a degree of 2, B has a degree of 3, as it has 3 edges, C has a degree of 3, as it also has 3 edges, and D has a degree of 3. E has a degree of 2, and F has a degree of 1. In graph H, vertex 1 has a degree of 3, vertex 2 has a degree of 2, vertex 3 has a degree of 3, and vertex 4 has a degree of 3. Vertex 5 has a degree of 2, and vertex 6 has a degree of 1. And ordering these numbers for each graph from highest to lowest gives us the degree sequence of each graph. And as we can see, the degree sequence of each graph is identical. Now let's look at the number of cycles in graph G and the cycle length. So in graph G, we can start at A, move to D. From D, we can go back to B. And from B, we're back at A. And that's a cycle of length 3, so that's a C3 cycle. And then we can start at vertex B, move to C, C to D, and D returning to B. And that's another C3 cycle. And then I can also see one which starts at A, goes to D, then to C, on to B, and back to A. And that's a C4 cycle. And then in graph H, we can start at vertex 1, go to 2, 2 to 3, and then back to 1 again. We can also start at vertex 1 again, go to 4, and then to 3, back to 1 again. And so that's 2 separate cycles of length 3. So 2 C3 cycles. And there's another one I can see. If we start at vertex 1, go to 4, and then 4 to 3, and 3 to vertex 2, and vertex 2 back to vertex 1. And that's a cycle of length 4. So it's a C4 cycle. I don't see any other cycles. So as we can see, graph H and graph G have an equal number of cycles, and each cycle is of equal length. And the final part is to map the vertices of graph G to the vertices of graph H via their edges. So we can see in graph G that vertex F has one edge, and in graph H, vertex 6 also has one edge. And these are the only 2 vertices in each graph that have one edge. And so we can map vertex F to vertex 6. And we can see in graph G that vertex F connects to vertex E, which is a degree 2 vertex. And in graph H, vertex 6 connects to vertex 5, which is also a degree 2 vertex. And therefore, vertex E maps to vertex 5. And in graph G, vertex E connects to vertex C, which is a degree 3 vertex. And in graph H, vertex 5 connects to vertex 4, which is a degree 3 vertex. And so we can map vertex C in graph G to vertex 4 in graph H. And of the remaining unmapped vertices, in graph G, there is only one vertex with a degree of 2, and similarly in graph H. In graph G, vertex A is a degree of 2, and in graph H, vertex 2 is a degree of 2. And therefore we can map vertex A to vertex 2. And now looking at what's left, we have in graph G we have B and D, and in graph H we have 1 and 3. And all these vertices have a degree of 3. In graph G, both vertices B and D connect to A and C, and they also connect to themselves. And in graph H, vertices 1 and 3 both connect to vertices 2 and 4, and also connect to themselves. And so we can map vertex B to vertex 1 and vertex D to vertex 3. Now some of you may have mapped B to 3 and D to 1. Is that wrong? Not at all. In graph theory, we call this an automorphism. As long as your mapping preserves the edges, meaning if B and D are connected in graph G, their partners 1 and 3 must be connected in H. Your isomorphism is valid. So we've proved that there is an isomorphic relationship between graphs G and H. In this example, let's check for an isomorphism between graphs G and H. As usual, if you'd like to play along, pause the video now. We first need to demonstrate that the number of vertices in graph G is equal to the number of vertices in graph H, and that the number of edges in graph G is equal to the number of edges in graph H. And so beginning with vertices, in graph G we have 1, 2, 3, 4 and 5. And in graph H we have 1, 2, 3, 4 and 5. The number of vertices in each graph is 5 and therefore equal. And now moving on to the number of edges in each graph. In graph G we have 1, 2, 3, 4, 5, 6, 7. And in graph H we have 1, 2, 3, 4 and 5. And so the number of edges in each graph is not equal. And so in this case, there is not an isomorphic relationship between graphs G and H. In graph theory, getting from vertex A to vertex B isn't just about the destination. It's about the rules you follow to get there. The words walk, trail and path are often used interchangeably, but on an exam, mixing these up will cost marks. Think of these as navigation laws. Some allow you to revisit streets, some allow you to revisit intersections, and some forbid both. In this video, we're going to break down the specific constraints of each, moving from the most flexible to the most restrictive. I've included chapters in the description so you can jump to a specific definition, but I recommend watching the examples in order to see how the rules stack up. Let's get started. A walk is the most basic sequence of edges and vertices. There are no restrictions here. You can traverse the same edge multiple times, and you can revisit the same vertex as often as you like. It's like a tourist wandering aimlessly around a city. They can walk down the same street twice if they want. Let's look at this example. We have 3 vertices, A, B, and C. These are connected by 3 edges, E1, E2, and E3. So we can do a walk from A to B, from B to C, from C back to B, and then from B back to A. Notice we went from B to C, and then back to B. We used the edge E2 twice, and visited vertex B twice. And this is perfectly legal in a walk. Now let's add a rule, the law of the trail, in which no edge can be repeated. You can still visit the same vertex more than once. And to use a navigation analogy, you cannot walk across the same street twice. So look at this bow tie shaped graph. We have vertices A, B, C, D, and V. Vertices A, B, and CD meet in the center at vertex V. Let's look at this trail. We can go from A to B using E1, from B to V using E2, from V to C using E4, from C to D using E5, from D to V using E6, and then from vertex V back to vertex A using E3. And so every edge we used was unique. We used all of them without repeating a single one. And in doing so, we hit vertex V twice and ended back at A. In a trail, repeating a vertex is always allowed, as long as the edges are new. If I now try and go from vertex A to vertex B again, using edge E1, the trail breaks, as I've used edge E1 for a second time. In graph theory, a path is the most restricted movement. With a path, nothing repeats. So you can't repeat an edge, and you cannot repeat a vertex. Once you leave a vertex, you can never go back to it. On this graph, in the shape of a square, a path would be from vertex A to vertex B via edge E1, from vertex B to vertex C by edge E2, and then from vertex C to vertex D by edge E3. So in this case, every vertex is new and every edge is new. If I were to go from vertex D to A using edge E4, I would be revisiting vertex A. And at that moment, it ceases being a path. Before we look at some challenges, Let's summarize what we've just learnt. So with a walk, we can repeat edges and vertices. With a trail, we cannot repeat edges, but we can repeat the vertices. And with a path, we cannot repeat edges or vertices. Now let's take a look at some challenges. So for challenge 1, let's look at this sequence. We have 4 vertices, A, B, C, and D. And we go from A to B, B to C, C to B, and B back to D. So there are 2 questions here. First one is, why can this never be a path? And the second one is, under what specific condition could this be considered a trail? If you want to play along, pause the video now. So is this a path? The answer is no, because vertex B is repeated. In a path, every vertex must be unique. Now the second question, is this a trail? Well, that depends on whether there are 2 edges connecting vertex B and C, so effectively making it a multigraph. If there are 2 edges, we could go from A to B, from B to C using one edge, and then from C back to B using a second edge, and then from B to D. So in this case, no edge has been repeated, so we'd have a trail. If, however, we had this scenario where there's just a single edge between vertex B and vertex C, so we could go from A to B, B to C, and then using the same edge from C to B, and then from B to D. And in this scenario, it would be classified as a walk because we've used the same edge twice. Let's say we have a graph with 2 vertices, so A and B, and between A and B we have 3 edges. Take a look at the sequence, A to B, B to A, and A to B. Is this a path or a trail? Pause the video now if you want to play along. Okay, let's follow the sequence. So we travel from A to B using this edge, and then B back to A using the edge in the middle, and then from vertex A back to vertex B using the bottom edge. So we've used all edges just the once, but we've used the vertices more than once. So therefore it cannot be a path, as every vertex we use must be unique. So it's therefore a trail, because although we've repeated some of the vertices, we've used the edges only once. Let's look at this graph. We have 9 vertices labelled 1 to 9, and they are joined up in a grid formation with 12 edges. And so in this formation, what is the maximum number of vertices you can visit in a single path? And for the second question, if we stay on the same graph, what is the maximum number of unique edges you can travel in a single trail? If you'd like to play along, pause the video now. So for a path, we can visit a vertex once and travel across a single edge just the once. So let's start at vertex 1. We can travel from vertex 1 to 2, from 2 to 3, from 3 to 6, from 6 to 5, from 5 to 4, from 4 to 7, from 7 to 8, and from 8 to 9. So in doing this, we've visited every vertex once, and most importantly, we haven't used any edges twice. So in this case, the maximum number of vertices is 9. Now let's look at the maximum number of edges we can use in a single trail. So let's start at vertex 2 and move to 5, and then 5 to 4, 4 to 1, 1 to 2, 2 to 3, 3 to 6, 6 to 5, 5 to 8, 8 to 9, and 9 to 6. At vertex 6, we have nowhere further to go without using an edge twice. And so if we count up the number of edges we've used, we get a total of 10. And so 10 is the maximum number of unique edges that we can travel in a single trail on this particular graph. In this next challenge, we have 6 vertices and 10 edges. And the question is, what's the maximum number of unique edges you can travel in a single trail? And if you think you know the answer, leave a comment in the comment section below. In this video, we're diving into connectedness and components related to graph theory. We'll learn how to identify weak links in a network and how to calculate exactly how much pressure a graph can take before it snaps. So let's get started. First, let's distinguish between being neighbours and being reachable. In a graph, two vertices are said to be adjacent if they share a direct edge, and a graph is said to be connected if a path exists between every pair of vertices. In this graph on the whiteboard, vertices 1 and 2 are adjacent, as they share a direct edge. Vertices 1 and 4 are not adjacent, but they are connected, because you can travel from vertex 1 to vertex 2, vertex 2 to vertex 3, and finally vertex 3 to vertex 4. If a graph is not connected, it's made up of a series of islands called components. The graph on the whiteboard is in the shape of two triangles with a total of 6 vertices. Together, they form one disconnected graph with 2 components. Let's now look at vertices and edges on a graph that, when removed, increase the number of components on a graph. A bridge, or cut edge, is an edge that, if removed, increases the number of components, while a cut vertex is a vertex that, if removed, breaks the graph apart. So if we look at the graph on the whiteboard, we have a star graph. We have one central vertex, so that's vertex number 4, that is connected to all the other vertices. If vertex 4 is removed, it has the effect of breaking the graph up into 3 components. And so vertex 4 is a cut vertex. Every edge that connects vertex 4 to the other vertices is a bridge or cut edge. If I remove any one of these, so here I've removed the edge that connects vertex 1 and 4, it has the effect of increasing the number of components. So this graph now contains 2 components. A graph is k vertex connected if it stays connected after removing any k-1 vertices. For this to be the case, it must contain more than k vertices, and the size of the minimum vertex cut, so the smallest set of vertices whose removal disconnects the graph, is at least k. So in this C4 graph on the whiteboard, if we remove one of the vertices, the remaining 3 vertices are still connected. If a second vertex is removed, the remaining 2 vertices are isolated. And so this graph is 2 connected. A graph is k edge connected if it remains connected after deleting any k-1 edges. This measures the minimum number of links that must fail to break the network. So in our C4 graph, if we remove one of the edges, the graph is still connected. If we now remove a second edge, we can isolate vertices, as is the case here, and disconnect the graph, as in this case. Therefore, a C4 graph is 2 edge connected. Let's now take a look at some challenges. In this first challenge, we have a graph with 8 vertices, and our task for this challenge is to find the bridge and the cut vertices. If you'd like to play along, pause the video now. So to find the bridge, we're looking for an edge that, if removed, increases the number of components. So effectively makes this connected graph a disconnected graph. So if we look at the edge that connects vertex 3 and vertex 6 and remove it, we now have a disconnected graph with 2 components. So this is the bridge or cut edge of this particular graph. And now let's look for the cut vertices. If we remove vertex 3 from the graph, we see that the graph once again breaks into 2 components. And this is also true if we remove vertex 6. And so on this graph, the cut vertices are vertex 3 and vertex 6. In this next challenge, we have a K5 graph. So we have 5 vertices and they all connect to each other. And our task is to find the vertex connectivity. So we're looking for the value of k in vertex connected. If you'd like to play along, pause the video now. So for this challenge, what is the minimum number of vertices we need to remove before the graph becomes disconnected? Let's start by removing vertex 5. So once vertex 5 is removed, we see that the graph is still connected. So let's continue by removing vertex 4. After removing vertex 4, we still have a connected graph. So let's remove vertex 3. After removing vertex 3, we still have a connected graph with two vertices, vertex 1 and vertex 2. So now let's remove vertex 2. And so removing vertex 2 finally isolates one of the vertices. And so this K5 graph is 4 vertex connected, as we needed to remove 4 of the vertices before we isolated a component. In this third challenge, we have a twin triangle structure containing vertices 1 to 6. The triangles are linked by just two edges, one between vertex 1 and 4, and a second between vertex 2 and 5. The question is simple. What is the edge connectivity of this graph? If you'd like to play along, pause the video now. So edge connectivity is the minimum number of edges we need to remove to disconnect the graph. So let's look at how we do this. If we remove the edge between vertex 1 and 4, we see that the graph is still connected with the edge between vertex 2 and 5. So let's remove this edge. And so now the graph is disconnected. So that's a cut set of size 2. Look at vertex 3 and vertex 6. They each have a degree of 2. And so we could also remove these edges, starting with vertex 3, and this would also disconnect the graph. This would also be the case for vertex 6. Removing these two edges would disconnect the graph. And so we can conclude that this graph is two-edge connected, as we need to remove a minimum of 2 edges to disconnect the graph. So in this graph, what about the vertex connectivity? If I wanted to disconnect this graph by removing vertices instead of edges, what is the minimum number of vertices I'd have to remove? If you think you know the answer to this, drop a comment in the comment section below. In this tutorial, I'm going to take you back to 1735, to the city of Königsberg, a city in Prussia, now Kaliningrad in Russia. It was divided by the Pregel River into 4 parts, a north bank, a south bank, and 2 islands, the large east island and the smaller west island. The north and south bank of the river were connected to the islands by bridges, and there was one bridge that connected the islands together. The locals had a game. Could you walk through the city, crossing every bridge exactly once and only once? They failed for decades. Let's take a look at the map and see why. On the north bank, we have 3 bridges, 1 to the east island and 2 to the west island. On the south bank, we also have 3 bridges, 1 to the east island and 2 to the west island. On the east island, we have 3 bridges, 1 to the north bank, 1 to the south bank, and 1 to the west island. And on the west island, we have 5 bridges, 2 to the north bank, 2 to the south bank, and 1 to the east island. Let's now have a few attempts at achieving what the locals couldn't. So let's start on the north bank and cross over to the east island using this bridge. And then we can head over to the west island and then back up to the north bank on this bridge. And then we can come back down onto the west island using this other bridge. And then we'll head to the south bank. And then from the south bank, we'll go back onto the west island. And now look, we've used 6 bridges and we're stuck on the west island. There's no way of using this bridge. So let's have another go. This time we'll start on the west island and we'll head up to the north bank. And from the north bank, we'll head back down to the west island and cross over this bridge to the south bank. And then we'll use this bridge to get back onto the west island. And the bridge between the west and the east island to take us onto the east island. Now we have a choice. We can head to the north bank or the south bank. So let's head to the north bank. And now we're stuck again. We've used 6 bridges, but the only way of getting to this bridge is to reuse one of the other bridges. So again, we failed. Let's have one final attempt. So this time we'll start on the south bank
and we'll head across this bridge to the West Island. Then we'll go from the West Island to the East Island, and we'll use this bridge to get back onto the South Bank. And we'll use this bridge to go back onto the West Island, and this bridge to take us to the North Bank, and this bridge to take us back onto the West Island. So now we're stuck on the West Island, and we still haven't used this bridge. The only way we can use this bridge if we reuse one of the other bridges. So once again, we failed. One day, a man named Leonhard Euler realized the city didn't matter. He turned the land into vertices and the bridges into edges. He counted the degree of each vertex. So that's the number of edges associated with each vertex. So the North Bank has 3, and the South Bank also has 3. The West Island has 5, and the East Island has 3. Think about any vertex that is not your start or end vertex. It's a pass-through point. To use an edge to get in, you need one to get out. That's a pair. Because every entry needs an exit, these vertices must have an even degree. If it's odd, you eventually enter and have no way to leave. This brings us to the definition of an Eulerian path or trail. This is a route in a connected graph that visits every edge exactly once. It's possible if and only if the graph has exactly 0 or 2 vertices with an odd number of degrees. I say connected graph because if the graph is in 2 separate pieces, you obviously can't walk between them. And I use the word trail because in graph theory, a trail means we never repeat an edge, which is at the heart of this puzzle. So why are we allowed 2 vertices with an odd number of degrees? This is because the start and end are the only ones allowed to be unpaired. You leave the start vertex using one edge, and you enter the end vertex using one edge. Let's see what we had in Königsberg. In Königsberg, we had 4 vertices with an odd number of degrees. So the North Bank had a degree of 3, the South Bank had a degree of 3, the West Island had a degree of 5, and the East Island had a degree of 3. And so the maths says that to achieve what the locals wanted to achieve was impossible. But what about ending where we started and using all the edges once only? Well, this brings us to the definition of an Eulerian circuit. And so an Eulerian circuit is an Eulerian trail that starts and ends at the same vertex. It's possible if and only if every vertex has an even number of degrees. In a circuit, the start and end vertex are the same. You leave at the beginning and enter at the end. This forms a pair. If there is one vertex with an odd number of degrees, the loop cannot be closed. Let's now take a look at some challenges to demonstrate these concepts. Let's take a look at this graph. We have 6 vertices numbered 1 to 6. And the question we're asking, is it an Eulerian path or an Eulerian circuit? If you'd like to play along, pause the video now. So the key to this one is knowing the degrees of each of the vertices. The degree of vertex 1 is 4, as it has 4 edges. And similarly, the degree of vertex 2 is 4, as it also has 4 edges. The degree of vertex 3 is 3, as it has 3 edges. And similarly, the degree of vertex 4 is 3, as it also has 3 edges. Now the degree of vertex 5 is 4, as it has 4 edges. And the degree of vertex 6 is 2, as it has 2 edges. So we have 2 vertices, so that's vertex 4 and vertex 3, with odd degrees, so 3 and 3. All the other vertices have even degrees. So in an Eulerian path or trail, we're allowed 2 vertices with an odd number of degrees. So let's see if we can follow this trail and use every edge once. So we need to start at one of the vertices which has an odd number of degrees. So let's start at vertex 4 and we can go to 5, from 5 to 3 from 3 back to 4, from 4 to 1, from 1 to 5, from 5 to 2, from 2 to 1, from 1 to 6, from 6 to 2, and then from 2 to vertex 3. So we've used up all the edges and all the edges only once. And so this is an Eulerian path or trail. So why can't it be an Eulerian circuit? Well, in Eulerian circuits, the degree of every vertex has to be even. And in our case, we have 2 vertices with an odd number of degrees. So let's look at this graph. Again, we have 6 vertices, and we want to know whether it forms an Eulerian path or trail or Eulerian circuit. If you'd like to play along, pause the video now. So let's look at the degree of each of the vertices. So vertex 1 has a degree of 2, vertex 2 has a degree of 3, vertex 3 has a degree of 2, and vertex 4 has a degree of 2. Vertex 5 has a degree of 3, and vertex 6 has a degree of 2. So we have 2 vertices with an odd number of degrees, and all the rest have an even number of degrees. So that tells us that it's an Eulerian path or trail. So let's see if we can follow it. So we need to start at one of the vertices with an odd number of degrees. So let's start at vertex 2 and travel to vertex 1. From 1 we can go to 6, from 6 to 5, from 5 back to 2, from vertex 2 to vertex 3, and then from vertex 3 to vertex 4, and finally from vertex 4 to vertex 5. So we've used every edge once. So why can't it be an Eulerian circuit? Well, 2 of the vertices have an odd number of degrees, and for it to be an Eulerian circuit, all vertices need to have an even number of degrees. In challenge 3, we have 5 vertices. All vertices connect to each other with an edge. So the question is, does this form an Eulerian path or an Eulerian circuit? If you'd like to play along, pause the video now. So the first thing to notice is that each vertex has a degree of 4. So that should tell us that it's both an Eulerian path and an Eulerian circuit. So let's prove this. So for it to be a circuit, we need to start and finish at the same vertex and use all the edges only once. So let's start at vertex 4 and travel to 1, then to 2, and on to vertex 3, and from vertex 3 to vertex 1, and then from vertex 1 to vertex 5, from vertex 5 to vertex 3, from 3 to vertex 4, from 4 to 5, from 5 to 2, and then from vertex 2 back to vertex 4 where we started. So this graph ticks both boxes. So in this challenge we have 9 vertices, and the question we want to answer: is it an Eulerian path? Is it an Eulerian circuit? Or maybe it's not either. If you think you know the answer, let me know in the comments section and leave a reason why. In earlier videos on graph theory, we've focused heavily on the properties of edges and how to traverse every single one on a graph. But in this video, we're shifting our focus to the vertex set. We are going to explore Hamiltonian cycles and paths. This is a field of graph theory where the vertex is the primary constraint. It governs how we model network efficiency and computational logic. While the rules are deceptively simple, the search for these structures remains a challenge in the field of mathematics. Let's look at the board and define the formal requirements. We're defining 2 specific structures based on the vertex set of a graph. The first one is a Hamiltonian path. It's a sequence of edges that visits every vertex in a graph once and only once. And the second is a Hamiltonian cycle, which is a Hamiltonian path that returns to the starting vertex. A graph is only called a Hamiltonian graph if it contains a Hamiltonian cycle. Simply having a Hamiltonian path is not enough. To be a Hamiltonian graph, you need the full set. The path must be able to close into a cycle. I have 2 different graphs on the board. Let's apply these definitions. And so starting with the graph on the left of the board, let's see if it's a Hamiltonian path or a Hamiltonian cycle. So we can begin at vertex A and move along the edge to vertex B and then cross to vertex C. From C, we can move to D and from D to E. So now we visited every single vertex in the graph. However, there's no way back to our starting vertex A. So this is a Hamiltonian path, as there's no edge connecting vertex E to vertex A. So there's no cycle, and therefore it's not a Hamiltonian graph. Now let's look at the second graph on the right of the board. Let's start at vertex 1 and see if we can visit every vertex once and only once and return to vertex 1. So beginning at vertex 1, we can travel to 2, and then from vertex 2 we can use the edge to move to vertex 3, and from 3 we can move to 4, from 4 to 5, and then there's an edge that will take us back from vertex 5 to vertex 1 again. So this is a Hamiltonian cycle because this graph contains the full set. It has the path and the cycle. It's therefore classified as a Hamiltonian graph. In a Hamiltonian path or cycle, our mission is to visit every vertex. Think of the vertices as cities and the edges as roads. If your goal is to visit every city once, you only need enough roads to get you from A to B to C. If there are 5 different highways between 2 cities, you don't need to drive on all of them to say you visited the city. In fact, if you tried to use every single edge in a complex graph, you'd be forced to visit the same vertex multiple times, which breaks our primary rule. In Hamiltonian maths, edges are just tools to reach the vertices. Once the vertex is checked off, the extra edges are mathematically irrelevant. So our vertex rule, where we visit every vertex once and only once, means that we can only use an edge once. To use an edge for a second time, you would need to have to travel from vertex A to vertex B again. But to do that, you'd have to be standing at vertex A for a second time. The moment you step back onto a vertex you've already visited, the sequence is no longer Hamiltonian. Therefore, the once and only once rule for vertices automatically limits every edge to a single use as well. Gabriel Dirac provided a famous sufficient condition to help us determine whether a graph was a Hamiltonian graph. Dirac's theorem states, for a graph with n vertices where n is greater than or equal to 3, if every single vertex has a degree of at least n divided by 2, then the graph is guaranteed to be a Hamiltonian graph. Let's apply this theorem to the graph on the left of the board. So we have 5 vertices, so n is equal to 5, and n is greater than or equal to 3. If we divide 5 by 2, we get 2.5. Now we can't have half an edge, so we round this up to 3. And so to guarantee that this is a Hamiltonian graph, every single vertex needs to have a degree of at least 3. So we can see that vertex A has a degree of 1, B has a degree of 2, C has a degree of 2, D has a degree of 2, and E has a degree of 1. So using this theorem, we cannot guarantee that the graph on the left of the board is a Hamiltonian graph. And as we saw, it's not. And if we apply the theorem to the graph on the right of the board, which again has 5 vertices, so n is equal to 5, n divided by 2 is 5 divided by 2, which again is 2.5, and we round this number up to 3, as we can't have half an edge. And so for this to be guaranteed to be a Hamiltonian graph, every vertex has to have a degree of at least 3. So let's look at the vertices. And as you can see, every single vertex has a degree of 4. So this graph is guaranteed to be a Hamiltonian graph. And as we saw, it actually is. But remember, this theorem provides a sufficient condition, not a necessary one. So we might have a graph that fails Dirac's theorem, but it's still a Hamiltonian graph. Now let's look at the famous Peterson graph. It has 10 vertices and 15 edges. And so it's quite easy to trace a Hamilton path here. So let's trace one. So remember, we need to visit every vertex once. So let's start at the top vertex. So there we have it. Every vertex has been visited, but do we have a Hamiltonian cycle and therefore a Hamiltonian graph? The answer is no. No matter how you try to connect these 10 vertices, you can never return to the start without repeating a vertex. So because it has a path but lacks a cycle, the Petersen graph is not a Hamiltonian graph. If you think you can connect them up, have a go at it and let me know how you get on in the comment section. However, the Petersen graph is what's known as a hypo-Hamiltonian graph. To be a hypo-Hamiltonian graph, a graph must satisfy two distinct conditions. So firstly, the graph itself is not a Hamiltonian graph, and so it doesn't contain a Hamiltonian cycle. However, if you remove any single vertex and the edges connected to it, the remaining graph suddenly becomes a Hamiltonian graph. The Petersen graph is the most famous hypo-Hamiltonian graph in existence. As stated in the demo, the full 10 vertex graph has no Hamiltonian cycle, and I hope you found that to be the case when you tried it yourself. If you delete any one vertex, you're left with 9 vertices. Those remaining 9 vertices will always have a Hamiltonian cycle. So let's try it. So I've deleted a single vertex, so we now have 9 vertices. So we should now have a Hamiltonian cycle. Let's give it a go. And there we have it. We started at the top vertex and passed through every vertex once and ended up back where we started. And so the Petersen graph is a hypo-Hamiltonian graph. And so to finish off, let's have a look at some challenges. So in this first challenge, we're asked, if a graph has 20 vertices, what is the minimum degree each vertex must have to guarantee it's a Hamiltonian graph? If you'd like to play along, pause the video now. So according to Dirac's theorem, in a graph with n vertices, where n is greater than or equal to 3, if every single vertex has a degree of at least n divided by 2, then the graph is guaranteed to be a Hamiltonian graph. So in the graph described here, n is equal to 20, but 20 divided by 2 is equal to 10. So in this graph, for it to be guaranteed a Hamiltonian graph, then each vertex must have a degree of at least 10. In this second challenge, we have a graph with 6 vertices. Can you find a Hamiltonian cycle, a Hamiltonian path, or maybe neither? If you'd like to play along, pause the video now. So to find a Hamiltonian cycle, we will also find a Hamiltonian path. And to find a Hamiltonian cycle, we need to find a path that visits every vertex once and finds its way back to the vertex at which we started. So let's have a go. So we can start at vertex 6 and head to vertex 1. From vertex 1 to vertex 2, from vertex 2 to vertex 5, and then from vertex 5 to vertex 4, and from 4 to 3. And finally, we can move from vertex 3 and return to vertex 6, which is where we started. So this is therefore a Hamiltonian cycle, and therefore a Hamiltonian graph. For challenge 3, let's look at this graph. Again, it's got 6 vertices. Can you find a Hamiltonian cycle or a Hamiltonian path? If you'd like to play along, pause the video now. So let's see if we can visit every vertex once. We can start at vertex 4, travel to vertex 6. Now we have 4 choices. So let's head out to vertex 2. And now look what happens. We're stuck at vertex 2 because if we go back to vertex 6, it means that we visited vertex 6 twice. And it doesn't matter where you start on this graph, as you won't find a Hamiltonian path or cycle. So let's look at this graph. We have 8 vertices arranged in 2 columns. The first column contains 3 vertices and the second column contains 5. Each vertex in the first column connects to every vertex in the second column. So we have a total of 15 edges. Can you find a Hamiltonian path or cycle in this graph? If you say yes, you can, make a list of the vertex sequence that forms the cycle or path, and let me know what it is in the comments section. In this video, we're looking at how we can represent the graph using matrices. While a visual diagram is great for us to look at, computers and algorithms need a more structured way to handle graph data. That's where the adjacency matrix and the incidence matrix come in. First, let's look at the adjacency matrix. This is a square matrix that tells us which vertices in the graph are connected to each other. If we have n vertices, we'll have an n by n matrix. So that's n rows and n columns. For a simple graph, the entry in row I and column j is 1 if there's an edge between vertex I and vertex j, and 0 if there isn't. And in an undirected graph, the main diagonal is all zeros. And this tells us there are no loops, meaning no vertex is connected to itself. And the sum of any row or column gives us the degree of that vertex. Let's now build an adjacency matrix. So looking at the graph on the board, we have 4 vertices and 5 edges that connect the vertices. Let's see if we can build an adjacency matrix from this. So for simplicity, I've labelled the rows and the columns V1 to V4, and this represents vertex 1 to vertex 4. So let's now take a look at each vertex and fill the matrix in. So if we look at vertex 1, there's no loop, and so it's not connected to itself. So we can place a 0 in row 1, column 1. Now if we look at vertex 1 and its connection to vertex 2, we'll see there's an edge E1. So we can place a 1 in row 1, column 2 to represent this connection. And if we look at vertex 1 and its relationship with vertex 3, we see there's an edge connecting them. And so we can place a 1 in row 1, column 3 of the matrix. And finally, for this row, we can look at vertex 1 and its relationship with vertex 4. And as we can see, there's an edge connecting the two vertices. So we can place a 1 in row 1, column 4. And now if we repeat the process for vertex 2 to 4, we see that we end up with a 4 by 4 matrix containing values of 0 and 1. If we now sum the rows of this matrix, the values we get represent the degree of each vertex. And so for vertex 1, it has a degree of 3. Vertex 2 has a degree of 2. Vertex 3 has a degree of 3. And vertex 4 has a degree of 2. And we can verify this by looking at the graph. The vertex 1 has 3 edges. Vertex 2 has 2 edges. Vertex 3 has 3 edges. And vertex 4 has 2 edges. Also notice the zeros along the diagonal of the matrix. This tells us that no vertex is connected to itself. So what if I did have a loop? What if vertex 1 was connected to itself, as in this scenario here? Well, the matrix would change. Row 1, column 1 would no longer contain a 0, but contain a 2. And the degree of vertex 1 would change from 3 to 5. Now let's turn our attention to the incidence matrix. Instead of showing vertex to vertex relationships, this shows vertex to edge relationships. If we have n vertices and m edges, we get an n by m matrix. Each column represents a single edge, and each row represents a vertex. In any column, you place a 1 for the 2 vertices that the edge connects, and a 0 everywhere else. Unlike the adjacency matrix, this one isn't usually square. And for a simple graph, every column will have exactly 2 1s, because every edge must connect 2 vertices. Let's now build an incidence matrix for the graph on the board. So to help our understanding, I've labelled the rows V1 to V4, representing vertex 1 to 4, and columns E1 to E5, representing the edges E1 to E5. So let's go through this column by column. So column 1 represents edge E1, and edge E1 connects vertex 1 to vertex 2. So we can place a 1 in row 1, column 1, and row 2, column 1 to represent this connection. And the other entries in this column will be 0, as edge 1 is only associated with vertex 1 and vertex 2, and has no association with vertex 3 and vertex 4. So looking at column 2, this represents edge 2, and this connects vertex 2 to vertex 3. So we can place a 1 in row 2, column 2, and row 3, column 2 to represent this connection, as row 2 represents vertex 2 and row 3 represents vertex 3. All other entries in this column are 0, as edge 2 is only associated with vertex 2 and vertex 3. And if we continue the process, we get the completed matrix shown here. And in a simple graph, as mentioned earlier, every single column in an incidence matrix must have exactly 2 1s, because every edge connects to exactly 2 vertices. And because of this, we see that the sum of each column is equal to 2. Now let's take a look at some challenges to consolidate the knowledge we've gained. So in this first challenge, we have a graph with 5 vertices. Let's see if we can build the adjacency matrix. If you'd like to play along, pause the video now. So we have a simple graph with 5 vertices, and we want to build the adjacency matrix. Now, because we have 5 vertices, the dimensions of our matrix is going to be 5 by 5. So it's going to have 5 rows and 5 columns. These represent the vertices and how they connect to each other. And as it's a simple graph with no loops, we have zeros on the diagonal. So let's go through it row by row. So for row 1, we're looking at vertex 1. And as there's no loop, we have a 0 in row 1, column 1. And it is connected to vertex 2 with an edge. So we have a 1 in row 1, column 2. There's no connection between vertex 1 and vertex 3. So in row 1, column 3, we place a 0. And vertex 1 is connected to vertex 4 with an edge. So in row 1, column 4, we place a 1. And vertex 1 is connected to vertex 5. So in row 1, column 5, we place a 1. And we can sum this row to get the degree of vertex 1. And as we can see, it has a degree of 3. And then moving on to row 2, where we're dealing with vertex 2, we see that vertex 2 is connected to vertex 1. So we can place a 1 in row 2, column 1. It has no loops. So there's a 0 in row 2, column 2. And vertex 2 is connected to vertex 3 with an edge. So we can place a 1 in row 2, column 3. And vertex 2 is not connected to vertex 4. So we place a 0 in row 2, column 4. And vertex 2 is connected to vertex 5 with an edge. So we can place a 1 in row 2, column 5. And if we sum this row, we get a value of 3. So that means the degree of vertex 2 is 3. And now to row 3, where we have vertex 3. So vertex 3 is not connected to vertex 1. So we place a 0 in row 3, column 1. Vertex 3 is connected to vertex 2 with an edge. Therefore, we place a 1 in row 3, column 2. And there's no loop. So there's a 0 in row 3, column 3. And vertex 3 is connected to vertex 4 with an edge. So we place a 1 in row 3, column 4. And there's no connection between vertex 3 and vertex 5. So we place a 0 in row 3, column 5. And if we sum this row, we see that vertex 3 has a degree of 2. Moving on to vertex 4, we see there's an edge between vertex 4 and vertex 1. So we place a 1 in row 4, column 1. There's no connection between vertex 4 and vertex 2. We place a 0 in row 4, column 2. Vertex 4 is connected to vertex 3 with an edge. So we place a 1 in row 4, column 3. There's no loop. So there's a 0 in row 4, column 4, and there's no connection between vertex 4 and vertex 5. So we place a 0 in row 4, column 5. And summing this row, we see that vertex 4 has a degree of 2. And moving on to vertex 5, we see it's connected to vertex 1 with an edge. So we place a 1 in row 5, column 1. It's also connected to vertex 2 with an edge. So we place a 1 in row 5, column 2. And there's no connection between vertex 5 and vertex 3. We place a 0 in row 5, column 3. And there's no connection between vertex 5 and vertex 4. Again, a 0 is placed in row 5 and column 4. And as there's no loop, we have a 0 in row 5, column 5. And summing this row, we see vertex 5 has a degree of 2. And for challenge 2, we have the same graph with 5 vertices. I've labelled its edges E1 to E6. And for this, we'd like to build the incidence matrix. So if you'd like to play along, pause the video now. So for the incidence matrix, this gives us information between the vertices and the edges. And the rows are linked to vertices and the columns are linked to edges. So if there are n vertices and m edges, the dimension of this matrix is n by m. And so we have 5 vertices and 6 edges. So the dimension of the matrix is 5 by 6. So let's go through this matrix column by column. So we'll start with column 1, and that relates to edge 1. So edge 1 is connected to vertex 1 and vertex 2 and not connected to the other 3 vertices. So we place zeros for vertex 3, 4 and 5. Edge 2 is not connected to vertex 1, so we place a 0 in row 1, column 2. It is connected to vertex 2 and 3, so we place a 1 in row 2, column 2, and row 3, column 2. So edge 2 is not connected to vertex 4 and 5, so we place a 0 in row 4, column 2, and row 5, column 2. And edge 3, there's no connection between edge 3 and vertex 1 and vertex 2. So we place a 0 in row 1, column 3, and row 2, column 3. Edge 3 connects vertex 3 and vertex 4. So we place a 1 in row 3, column 3, and row 4, column 3. And there's no connection between vertex 5 and edge 3. So we place a 0 in row 5, column 3. And moving on to edge 4, we see that it is connected to vertex 1. So we place a 1 in row 1, column 4. There's no connection between edge 4 and vertex 2 and vertex 3. So we place a 0 in row 2, column 4 and row 3, column 4. Edge 4 is connected to vertex 4. So we place a 1 in row 4, column 4. And edge 4 is not connected to vertex 5. So we place a 0 in row 5, column 4. And for edge 5, it is connected to vertex 1. So we place a 1 in row 1, column 5. It has no connection with vertex 2, 3 or 4. So we place zeros in row 2, column 5, row 3, column 5 and row 4, column 5. And edge 5 is connected to vertex 5. So we place a 1 in row 5, column 5. And for edge 6, we have no connection between edge 6 and vertex 1. So we place a 0 in row 1, column 6. Edge 6 is connected to vertex 2. So we place a 1 in row 2, column 6. There's no connection between edge 6 and vertex 3 and 4. So we place zeros in row 3, column 6 and row 4, column 6. And edge 6 is connected to vertex 5. So we place a 1 in row 5, column 6. And as we can see, the sum of the columns is 2, as each edge connects 2 vertices. In this next challenge, if the sum of row 3 in an adjacency matrix is equal to 4, what does that tell you about the graph? And if you'd like to play along, pause the video now. So this tells us that the degree of vertex 3 is equal to 4. And so it's connected to 4 other vertices. And for challenge 4, if we have a graph with 6 vertices and 10 edges, what are the dimensions of its incidence matrix? If you'd like to play along, pause the video now. So the dimension of an incidence matrix is given by n by m, where n are the rows in the matrix and m are the columns. And the rows in an incidence matrix relate to vertices and the columns relate to edges. So in this case, we have 6 vertices, so 6 rows, and 10 edges, so 10 columns. So we have a 6 by 10 matrix. In this video, we're exploring the subject of trees in relation to graph theory. Before we look at how they work, we have to define exactly what a tree is in the mathematical sense. A tree is a simple undirected graph that satisfies 3 specific conditions. The first is that it's connected. So there's a path between every single pair of vertices. The second is that it's acyclic. It contains no cycles or loops. And the third and final condition is that if a graph has n vertices, there are exactly n-1 edges. We specify a simple graph because we don't allow multiple edges between the same two vertices. If we had two edges between vertices 1 and 2 in the graph shown on the board, we'd have a cycle of length 2. And this would break our acyclic rule. And when we say the graph is undirected, this means that the edges are a two-way bridge with no arrows. So let's take a look at what is and isn't a tree. And to do this, we'll use the graph on the board. This graph has 4 vertices and 3 edges. As the graph has 4 vertices, n is equal to 4. And for this graph to be considered a tree, it needs to have n-1 edges. So where n is 4, n-1 is 3. And as we can see, it has 1, 2, 3 edges. So this graph is considered to be a tree. So in this scenario, I've added an additional edge that connects vertex 1 to vertex 4. And this creates a cycle. And so this graph on the board cannot be considered to be a tree. And in this scenario, we have our same 4 vertices, but this time we have 2 edges. The first connects vertex 1 to vertex 2, and the second connects vertex 3 to vertex 4. And this is a disconnected graph. And we know that for it to be a tree, the graph needs to be connected. So this graph as it stands is not a tree. In this graph, we have 4 vertices and 3 edges. So we have the correct number of edges related to the number of vertices. So n is 4 and n-1 is 3. However, it's not a tree for 2 reasons. Firstly, it has a cycle. So vertex 1 is connected to vertex 2, 2 to 3, and 3 back to 1. And secondly, it's a disconnected graph because vertex 4 is isolated. In computer science, we often draw trees vertically, known as rooted trees. At level 0, which is the root, we have a single vertex at the top of the graph. At level 1, we have the children branching from the root. At level 2, we have the grandchildren, and so on. We note that this is a connected acyclic graph, and this graph has 13 vertices and 12 edges. So the number of edges is 1 less than the number of vertices. These are often used to model data structures and create decision trees. In graph theory, a spanning tree is a subgraph of a connected, undirected graph that includes all of the original graph's vertices while being a tree, which means it's both connected and acyclic. And to find a spanning tree within a graph, we can use the break cycle method. So think of this as a redundant path. If you have 2 ways of getting from A to B, you can remove one way without losing connectivity. And you can do this by systematically breaking every loop. And eventually you arrive at a minimum number of edges needed to keep the graph connected. Spanning tree protocol, as used in networking, is a real-world example of where spanning trees are used. If an office has too many redundant cables, data can circle forever in switching loops. STP, or spanning tree protocol, breaks those cycles by turning off extra edges until only a single logical spanning tree remains. Let's look at the graph on the board and identify a spanning tree. So we have 4 vertices and 4 edges. So this graph is not defined as a tree. We also note we have a cycle. The vertex 1 is connected to vertex 2, which is connected to vertex 3, and 3 is connected back to vertex 1. So if we wanted to get from vertex 1 to vertex 4, at the moment, we could start at vertex 1, travel to 2, from 2 to 3, and from 3 to 4. We could also start at 1, travel to 3, and then go from 3 to 4. So we have 2 paths in getting from vertex 1 to vertex 4, and so one of them is redundant. And so to find the spanning tree, we need to break the cycle. If I now remove the edge that connected vertex 1 to vertex 3, I now have a spanning tree. As it contains all the original vertices, it's minimally connected, so it contains the smallest set of edges that can connect all vertices. It contains no cycles or loops, and there is exactly one unique path between any 2 vertices in the graph.
Every connected graph has at least one spanning tree, although most graphs contain more than one. Let's now consolidate what we've just learned and look at some challenges. So in this first challenge, we have two graphs. Which of the graphs is a tree and which one isn't, and why? If you'd like to play along, pause the video now. So for a graph to be considered a tree, the graph needs to be connected. So there needs to be a path between every single pair of vertices. And as we can see, both graphs comply with this. A tree also has to be acyclic, so it contains no cycles or loops. So let's have a look at the graphs. So in the graph on the left, I can see at least 3 cycles, from vertex 1 to vertex 2, from vertex 2 to vertex 5, and from vertex 5 back to 1. Also from vertex 1 to vertex 5, from 5 to 2, from 2 to 3, from 3 to 4, and from 4 back to 1 again. And from vertex 1 to vertex 2, from vertex 2 to vertex 3, from 3 to 4, and 4 back to 1. So this graph cannot be considered to be a tree. If we look at the graph on the right, it has no cycles. It's also connected. It has 6 vertices, so therefore n is equal to 6. And so for it to be a tree, it has to have n minus 1 edges. So n minus 1, where n is equal to 6, is equal to 5. So it has 1, 2, 3, 4, 5 edges. So this graph is a tree. For our second challenge, in this K5 graph, where we have 5 vertices, and all vertices are connected to each other, how many edges must you remove to create the spanning tree? If you'd like to play along, pause the video now. So this graph has many cycles, and so to find the spanning tree, we have to break those cycles by removing edges, and then we'll end up with the minimum number of edges required to connect the graph. So there's an obvious cycle around the edge of the graph, so let's break that cycle. So we'll remove the edge that connects vertex 1 to vertex 2. Now let's break this cycle shown here, and we'll do this by removing the edge that connects vertex 1 to vertex 4. And for this cycle shown here, we can break it by removing the edge that connects vertex 3 to vertex 4. And for the cycle shown here, we can break this cycle by removing the edge that connects vertex 2 to vertex 5. And for this cycle, we can remove the edge that connects vertex 2 to vertex 3. And the last cycle we need to break is this one shown here. And to break it, we can remove the edge between vertex 1 and vertex 5. And so we now have a subgraph of the original K5 graph. It's acyclic, meaning we've removed all the cycles. There's a path between every single pair of vertices. We have 5 vertices, so n is equal to 5. So the number of permitted edges is n minus 1, which in this case is 4. And so this is a spanning tree. And to get to it, we needed to remove 6 edges. And therefore, 4 edges is the minimum number of edges needed to keep the graph connected. For challenge 3, let's look at this graph, which is a 3-level tree with 7 vertices. If we add a 4th level, where every vertice from level 2 gets 2 children, we add 8 new vertices. How many edges will the new tree have? If you'd like to play along, pause the video now. So I've drawn the new graph and added a 4th level with 8 vertices. Now we don't really need to draw this graph to work this out, because the number of vertices in the new graph is 8 plus the 7 we already had. So n is equal to 15. And as this is a tree, the number of edges must be equal to n minus 1, where n is equal to 15. So the number of edges is 14. And we can count them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And for our 4th challenge, if a hydrocarbon molecule is modelled as a tree and has 30 atoms or vertices, how many chemical bonds or edges must it have? If you think you know the answer, let me know in the comment section. In this video, we're going to look at planar graphs. A graph is defined as planar if it can be drawn on a flat surface without any of its edges crossing. We're going to establish the mathematical law that determines whether a network can be drawn without these crossings. Look at this K4 graph on the board. It has 4 vertices and 6 edges. It has crossing edges in the center, which might suggest it's non-planar. However, if we redraw this diagonal edge around the outside of the square, the crossing is removed. Because a version exists where no edges cross, it's officially a planar graph. Planarity is about whether it's possible to draw a graph without crossings. To see where planarity fails, we look at the complete bipartite graph, known as a K33. In a bipartite graph, vertices are split into 2 sets, and edges only connect between those sets, never within the same set. So in this example, we have 9 edges in total. As we draw these connections, we find that at least one crossing is unavoidable. The graph is non-planar because it cannot be represented without edges intersecting. If you'd like to support this channel, you can now become a member to get early access to every video. To join, you can use the link displayed at the top of the screen, or just hit the join button right below this video. The primary tool for analyzing these networks is Euler's formula. It states that for any connected planar graph, the number of vertices v minus the number of edges e plus the number of faces f must equal 2. This is a strict requirement. If the calculation equals 2, the graph is planar and the edges do not cross. If the result is not 2, it indicates the graph is non-planar. To use this formula, however, we must first define the third variable, the face. A face is a region enclosed by edges. To explain this, I've drawn a graph with 4 vertices and 4 edges, creating a cycle. The interior region of this graph, shown in pink, is face 1, and the infinite face, face 2, is the entire area outside of the graph and beyond the edges. We must count the exterior region as a face for the formula to hold true. Now let's look at this graph. We have 6 vertices and 8 edges. Face 1 and face 2, so the blue and pink region, create triangle shapes, and face 3 in orange creates the shape of a rectangle. And I've marked in the infinite face, face 4, which is outside of the edges of the graph. Now let's apply Euler's formula to this graph. And so if we plug in the numbers for this graph, we have 6 vertices minus 8 edges plus 4 faces, and this equals 2. So we have mathematical confirmation that this graph is planar and can be drawn without crossing edges. To find the ultimate limit of a planar graph, we need to look at how edges and faces are linked. In a simple planar graph, every face must be bounded by at least 3 edges. Look at our graph on the board, shaped as a triangle. It has 2 faces, so an interior face shown in blue here, and the infinite face outside the boundary of the graph, shown in pink. If we now multiply the faces by that minimum requirement of 3, we get 3 multiplied by 2, which is equal to 6. You might ask, how can we count 6 when there are only 3 edges on the board? The answer is that every edge is doing 2 jobs. Each edge acts as a boundary for the internal face and a boundary for the infinite face. When we sum up the boundaries face by face, we count every edge exactly twice. And this gives us our first fundamental law, the total boundary requirement. So 3 multiplied by the number of faces cannot exceed the number of edges multiplied by 2. So therefore we have 3f is less than or equal to 2e. And in our graph on the board, shaped as a triangle, the maths is perfectly balanced. So we have 3 times the number of faces, so we have 2 faces, must be less than or equal to 2 multiplied by the number of edges, which is 3. And this gives 6 is less than or equal to 6. Now let's use this to find the general limit for all planar graphs. So if we start with Euler's formula, which is v minus e plus f is equal to 2, and rearranging to find f, we have f is equal to 2 plus e
minus v. And if we substitute f, where f is 2 plus e minus v, into our inequality 3f is less than or equal to 2e, we get 3 multiplied into the bracket of 2 plus e minus v is less than or equal to 2e. And expanding the brackets, we get 6 plus 3e minus 3v is less than or equal to 2e. And rearranging this gives us the number of edges must be less than or equal to 3 times the number of vertices minus 6. And this tells us that a graph with 3 vertices can have at most 3 edges. If you have a graph with 5 vertices, your budget is 9 edges. If you try and force a 10th edge into those 5 vertices, the maths proves the boundaries will fail and the lines must cross. Now let's look at some challenges to test our knowledge. So in this first challenge, we have a graph in a hexagon shape. The question is this a planar graph? Pause the video now if you'd like to play along. So for this to be a planar graph, Euler's formula would need to balance. So the number of vertices minus the number of edges plus the number of faces must equal 2. So we have 6 vertices minus the number of edges, which is also 6. So how many faces does this graph have? So we can see it has an interior face shown here and the infinite face indicated by the green area. And so we have 2 faces. So Euler's formula does in fact add up to 2. For challenge 2, suppose you are designing a network with 10 vertices and you're required to create 7 distinct enclosed regions. How many edges are needed to maintain planarity? If you'd like to play along, pause the video now. So this one's a bit of a trick question because it talks about 7 enclosed regions, meaning 7 interior faces. However, we mustn't forget about the infinite face. So in our equation, where the number of vertices minus the number of edges plus the number of faces is 2, if we plug in the numbers, we have 10 vertices, an unknown number of edges, we'll just call it minus e, plus the number of faces. Now we have 7 enclosed faces, but we mustn't forget the infinite face. So we need to add 1 to 7, and that gives us 8. And this should all add up to 2 to be a planar graph. And so if we solve this for e, we get e is equal to 16. So in the scenario described, we would need a total of 16 edges for this graph to be planar. And so for this third challenge, we have a K5 graph. So we have 5 vertices and 10 edges. The question is, can this graph exist as a planar graph? If you'd like to play along, pause the video now. So first, let's use Euler's formula to see how many faces a planar version of a K5 graph would need. So we have v minus e plus f is equal to 2. So we have 5 vertices minus 10 edges plus the number of faces must equal 2. So the number of faces would equal 7. Now let's check our boundary rule. We know that every face needs at least 3 edges to be enclosed, but every edge can only serve as a boundary twice. This gives us our limit, where 3 times the number of faces must be less than or equal to twice the number of edges. And so plugging in the numbers for this K5 graph, we have 3 multiplied by the number of faces it needs, so that's 7, must be less than or equal to 2 multiplied by the number of edges, which is equal to 10. And this gives 21 must be less than or equal to 20. So the maths has failed. To have 7 faces, we need 21 boundaries, but our 10 edges can only provide 20. We're exactly 1 short. Because the requirement exceeds the capacity, it's physically impossible to enclose those 7 faces in a planar graph. So therefore, a K5 graph is a non-planar graph. In this video, we're going to be taking a look at graph coloring and chromatic numbers. When we color the vertices of a graph, we must assign a color to every vertex so that no 2 adjacent vertices share the same color. By adjacent, we mean any two vertices connected by an edge. Think of it like a map. Countries sharing a border cannot be the same color or they'll blend together. The minimum number of colors needed to satisfy this rule is called the chromatic number and is denoted by the Greek letter chi. Let's look at the graph on the board and pick some colors such that we don't fall foul of the coloring rule. So I've picked the color blue for vertex 5, which means that its two adjacent vertices, 1 and 2, need to be a different color. And as they are adjacent to each other, as vertex 1 is connected to vertex 2 with an edge, they need to have two different colors. And so I've picked green for vertex 1 and pink for vertex 2. Now let's look at vertex 3 and 4. Vertex 4 is adjacent to vertices 1 and 3. So we can use blue for vertex 4, since vertex 1 is green and vertex 3 is yet to be assigned a color. Now for vertex 3, which is adjacent to vertices 2 and 4. We need to avoid the colors pink and blue. So let's make it green. And so we've colored the whole graph with 3 colors. So for this graph, chi of g is equal to 3. If you'd like to support the channel, you can now become a member to get early access to every video. To join, you can use the link displayed at the top of the screen or just hit the join button right below the video. Let's now look at some specific types of graphs and determine their chromatic numbers. So I've drawn a complete K5 graph on the board. In a complete graph, every vertex is adjacent to every other vertex, and therefore no two can share a color. And so the number of colors required is the same as the number of vertices. Therefore, chi of a K5 graph is equal to 5. And that number will increase or decrease depending on the number of vertices. I've drawn a complete bipartite or K33 graph on the board. In this type of graph, vertices are split into two sets, and no two vertices within the same set are adjacent. And because of this, we only need two colors to color the graph. So in this case, chi of the K33 graph is equal to 2. So its chromatic number is 2, indicating that only two colors are necessary. Let's look at the two cycle graphs on the board. On the left, we have a cycle graph with 4 vertices, so it's a C4 graph. And on the right, we have a cycle graph with 3 vertices, so it's a C3 graph. In a cycle graph, if the number of vertices is even, like the C4 graph on the left, we just need two colors, as there will only ever be 2 vertices that are adjacent to each other. And so in this particular case, chi of C4 is equal to 2. And in the C3 graph on the right of the board, where we have 3 vertices, we see it requires 3 colors, as each vertex is adjacent to 2 others. And so in this case, chi of C3 is equal to 3. And this applies to all cycle graphs, irrespective of the number of vertices. And so if a cycle graph has an even number of vertices, then the chromatic number is 2. If it has an odd number of vertices, then the chromatic number is 3. Now let's look at the 4-color theorem. This only applies to planar graphs, so graphs drawn without edges crossing. It states that for any planar graph, chi of g is less than or equal to 4. So no matter how complex the network, if it's a planar graph, 4 colors is the absolute ceiling for keeping adjacent vertices distinct. So I've drawn a planar graph on the left of the board. Let's see the limit in action. So in this graph, I can recycle some of the colors. Even if I have many vertices, they aren't all adjacent to one another. So as long as the graph is planar, so that is none of the edges cross, 4 colors is always the maximum number of colors you'll need. And in this graph, chi g is equal to 3. Now we've learnt about chromatic numbers, let's take a look at some challenges and see if we can work out the chromatic numbers of some specific graphs. So in this first challenge, we have a graph with 6 vertices. Let's see if we can color the graph and work out its chromatic number. If you'd like to play along, pause the video now. And so in this one, we
we have an outer cycle, which has an odd number of vertices and is equal to 5. And as we saw in cycle graphs, a cycle with an odd number of vertices will need 3 different colours, and all the outer vertices are adjacent to one central vertex. And so this requires a 4th colour. And so in this example, chi of g is equal to 4. And for challenge 2, we have one central vertex, which is connected to 5 other vertices. Let's see if we can work out its chromatic number. If you'd like to play along, pause the video now. And so in this graph, the central vertex, so vertex number 6, is adjacent to all other vertices. But the other vertices around the outside of the graph aren't adjacent to each other. And therefore we only need 2 colours. So chi of g is equal to 2. In this third challenge, we have a graph with 6 vertices. And the vertices are arranged such that we have an inner triangle and an outer triangle. Let's see if we can work out the chromatic number of the graph. If you'd like to play along, pause the video now. So this graph contains an inner triangle and an outer triangle. So we have 2 cycles with an odd number of vertices. So for the outer triangle, we can colour the vertices pink, blue and green. And for the inner triangle, we can use the same colours, but we need to shift them along once, as we have adjacent vertices between the inner and outer triangle. And so for this graph, chi of g is equal to 3. And for challenge 4, let's look at the Peterson graph and see if we can work out its chromatic number. If you'd like to play along, pause the video now. And so for the Peterson graph, we have 5 outer vertices forming a cycle. And as 5 is an odd number, we know that we need 3 different colours to keep the adjacent vertices distinct. And for the 5 inner vertices, each vertex is connected to 2 others. And so for the inner ring of 5 vertices, we only need 3 colours. We can use the same 3 colours as we use for the outer vertices, being careful to ensure that the colour of adjacent vertices between the outer and inner ring of vertices is different. And so for the Peterson graph, chi of g is equal to 3.